Alright guys, so again, when we are balancing a reaction, we want to write down the atoms on the reactant side and on the product side, and we want to write down how many there are present in the chemical equation. And ultimately, when we're balancing, what we want to achieve is the same number on both the reactants and the product side, alright? So the very first thing that I do, I write them out. And I do that in a symmetrical way so that it's easier for me to keep track. And I'm simply going to be looking at it and writing down how many there are of each. So over here, for carbon, we have 2. On the product side, we have 1. Hydrogen, we have 6 on the reactant side. We have 2 on the product side. And for oxygen on the reactant side, I have 2. And then on the product side, I have oxygen located here and here, right? In carbon dioxide and water. So what I like to do in a situation like that is to write them out separate. So 2 plus 1 when they're part of 2 different compounds. So that if I make a change to 1, I'm going to be able to easily see how that's impacting the total amount of atoms. All right, so here we have 2 plus 1, which is a total of 3. And then ultimately, all I'm going to be doing is matching them. And I'm going to be doing that with the help of coefficients. Coefficients, are going to be placed in front of the compound. And it's just going to be letting us know how many of that compound are present, okay? So, over here, we have 2 versus 1 for carbon. You're going to select the lesser number. In this case, the lesser number is 1. So you ask yourself, 1 times what is going to equal 2? What's the answer, you guys? 2, right? So given that the answer is 2, I'm going to place 2 right here. This is now going to become 2. But because I have that coefficient right there, it's going to impact the entire compound. So not only am I changing the quantity of carbons, but also of oxygens as well. So over here we have 2. So 2 times 2 is going to give me 4 plus 1. We have a total of 5. And you can see why I split them up in here. Then for hydrogen, we have 6 on the reactant side, 2 on the product side. So you ask yourself, all right, the lesser one is 2. 2 times what is going to give me 6? The answer? 3, right? Pretty straightforward there. So the answer is 3. I'm going to go ahead and add 3 right here. This is now going to be 6. But again, because I'm placing a coefficient here, not only am I impacting hydrogen, but also oxygen. So initially on the second atom right here for oxygen, I had 1. So I placed that 3 there. So now this becomes 3, right? Because 3 times 1 equals 3. So now I'm going to go ahead and add this up. 4 plus 3, we have a total of 7. So far, so good. Then for oxygen, on the reactant side, we have 2. On the product side, we have 7. Select the lesser number, 2. 2 times what is going to give me 7? The answer? 3.5, right? 3.5. 3.5. All right. Now, this is an issue because we have half of a molecule here in place, right? And whenever we're doing chemical equation and in nature, really, we cannot expect to see just half a molecule, all right? So we will have to then be able to convert that into a whole number. And how we're doing that, and if you've seen the video, you know what I'm talking about. If I write this 3.5, right, this is equivalent to 3 and 1/2. Would you guys agree? All right. So if 3.5 and 3.5 are the same thing, right, we don't want to focus on the 3 because that's already a whole number. So we want to convert this half into a full number. So what would I have to do here in order to convert that fraction into a whole number? Multiply by 2 or multiply by its inverse, right? So you can either do this, which is the exact same thing as this, right? So if you do this, then this is just going to give you 2 over 2, right? 2 over 2, which would give me a whole number. Ultimately, then, if you end up having half a number, right, a fraction in your chemical equation, then what you will have to do in order to convert that into a whole number, you're going to have to multiply that by 2. Now, if I multiply dioxygen by 2, right? I'm changing it by a factor of 2. I'm going to have to do the exact same thing for the entire chemical equation. And the reason for that, if you think about if you're making cookies, right, and you want to just make more cookies, you don't just add flour. If you're going to be increasing the amount of flour, you're also going to have to be increasing eggs and whatever else is needed in cookies, right? So with that said, I know I'm like over explaining this. In general, what you need to know is if you end up having 3.5 or whatever half a number, you're just going to have to multiply the entire thing by 2. And when I say the entire thing, I'm talking about the coefficient, the amount of molecules, not the subscripts, okay? So, for instance, I'm going to take this whole thing, multiply by 2, right? And so I have just 1 here because there's nothing written, which represents just 1, right? So 1 times 2 is going to give me 2. 2 times 3.5 is going to give me 7. 2 times 2 is going to give me 4. And 2 times 3 is going to give me 6. So then my final answer is going to be 2, right? 7, 4, and 6. Questions? Yes, ma'am.
Are you able to just put like the parentheses and then put the 2 on the outside instead of changing all the coefficients?
No.
You have to change all of them?
Yes.
Okay.
If you do that, it wouldn't be finished. It depends on how your lecture professor will grade it. Most of the time, they want to see the final answer. Thus, you'll have to write down the final. Normally, what you want to do is maybe rewrite it without even this parenthesis here with it too. So maybe like you would do this at the end. Any more questions? All right. Let's move on. So now let's discuss double displacement reactions. So in a double displacement reaction, we have 2 aqueous compounds, all right? And in general, what they're going to be doing is each compound is going to be switching their cations of one with the anion of the other, all right? So what's important to note, first of all, we need to understand what a cation is. So let me write that for you guys. So we have a cation, which is the positively charged ion, okay? Cation, positively charged. Anion is negatively charged. All right, how are you able to remember that? Where if you look at the word cation, right, it's got that T, which you can kind of think that represents a positive sign, right? And then you've got anions, which the word itself has a lot of N's. So you could think of that as a reminder for negative, right? So cation, positive, anions, negative. All right. When I say an aqueous solution, what is a solution? Solution is composed of a solute and a solvent, all right? The solute are the ionic compounds, and then the solvent is usually water. So let me write that down for you as well. Specifically today, we're going to be talking about precipitation reactions, which is a type of double displacement reaction. So, a precipitation reaction then would be a reaction in which we have 2 aqueous ionic compounds that will be generating or producing an insoluble product. All right? In other words, in a precipitation reaction, a solid will form. Okay? So, I'm gonna write this down again. All right. The insoluble product is going to be the precipitate. So insoluble and the precipitate is going to be represented with an S subscript for solid, right? And then the soluble part of the product is going to be the supernatant. Okay? And we will represent that with an AQ for aqueous. So how will we know? Once we generate the product, right, we could look at the solubility rules and we could identify whether the product is going to be aqueous or solid. Right? If you end up having two aqueous products, then no reaction is said to take place, right? No precipitation reaction, specifically. Because again, in a precipitation reaction, we have two aqueous ionic compounds that react to form an insoluble product, aka a solid. So if we don't see a solid forming, then no precipitation reaction occurs. This is something that you're going to be able to double check when you're doing your experiment, right? If you see that there is no changes, then you could also look at the solubility rules and see, hey, does this make sense? Does this match my observations? Do I have two aqueous products? And if so, then you could conclude that there is no reaction taking place, no precipitation reaction. So today, a lot of what we're going to be doing is taking observations. Specifically for part one, we're going to be doing double displacement reactions. Not all reactions are going to actually take place, and mostly you could double check that with the solubility rules. The solubility rules were posted on Blackboard are these guys right here, okay? So, any questions so far? All right. Let me move this down a little bit. All right. So with that said, let's go ahead and do an example. Here we have iron 3 nitrate and sodium hydroxide. These are my two reactants, right? The very first step is going to be for you to figure out what the products are going to be. So to figure out what the products are going to be, the first step would be to split them up and figure out what the charge is for each of those atoms, right? So some of them you guys were supposed to memorize, I believe, for lecture, right? So the most popular ones that you're gonna see over and over is gonna be nitrate, it's gonna be carbonate, it's gonna be phosphate. It's just some of the common ones, as well as hydroxide. You're just gonna see those appearing again and again. However, if you look at the chemical formula that they're giving you there, you should be able to also identify what the charges are. All right? Before I jump into this real quick, well, you know what? Let's continue with this, I guess. So the ones that you have to be wary of are going to be the transition metals. The ones that you're going to be seeing more often is going to be iron and copper. So iron and copper are going to be transition metals, which means that the charge could be either +1, +2, +3, right? But you're going to be able to identify that by looking at what it's reacting with, right? So here we've got the chemical formula. This is the final product, right? I should say product, but the final chemical formula is the final answer per se. Then we're going to be going a step back. In order to do that, I'm going to split them up. I'm going to have iron, and then I'm going to have nitrate, NO3. And then you guys, before we even focus on this, right, when we're splitting them up, the formula that you're seeing here is going to be, or is going to have a result charge of 0, which means that they're basically going to be crossing each other out to be stable and be 0, okay? So when you're doing that, again, going a step back, if you split them up, you could think of, I'm just going to represent the charges with an X for iron and then a Y for nitrate. Normally when you've got these charges, what you're going to see is this charge will go down and across, and then this charge will go down and across, okay? Then when you're looking at the final formula here, right? Because if I do this, just with my example, I'm going to have iron, that Y, which will be a charge, right, will come down here, now becomes a subscript, and then we have NO3, and that X, if you have a polyatomic ion, you're going to have to write the parentheses, and then the charge will come down. So essentially, if you're looking at the final answer that they're giving you, right, you could identify what the charges were. So if you're seeing something here, right, we know that it's here because it came from up here, just like we did in this example below. And same thing, if we see something down here, we know that it's there because it came from up here, okay? So given that, you guys, what is the charge of iron here? +3. And then nitrate, we don't see anything here, right? So it must be a 1. All right. And then really, if you did what I just did, which is take these and go down and across and go down and across, you'll have this 3 down here, right? You have nothing because you don't write the 1. And what you should see is that this exactly matches this. And that's what we're seeing, right? So that's how you identify the charges. Alternatively, when you figure out the charges, you could also look at them and say, okay, if I know, you could look at this formula right here, right? And if you've memorized nitrate, you know that the charge is -1. So you could look at it and say, okay, I have 3 nitrates, so 3 -1s, right? Let me represent that in a little drawing. So I have NO3, NO3. This is horrible. Let me rewrite that. I have NO3 -1, NO3 -1, NO3 -1. All right, if we count for the charges, how many do we have? -1, -1, -1, total of -3, right? You guys are not even seeing that, right? -1, -1, -1, a total of -3. So as you see, there are 3 in the compound that they're giving you, in the chemical equation that they're giving you. There are 3 nitrates per each 1 iron. And again, we know that the charges will have to cross out, okay? So if we have 3 nitrates, which is equivalent to a total charge of -3, and we have just 1 iron that is required to cross that out, what must the charge of iron be to cross out this -3? +3, right? So that's another way that you could think about it. 1 + 3 iron will cross out 3 -1 nitrates. Okay? So you could think of it whatever makes the most sense for you. I think the fastest way for me personally is just to cross down the numbers. with that said, you have to be careful because some people will, if they're just doing the crossing, they will take this 3 and go up and across with that. And you just have to be careful because this 3 is part of the polyatomic compound, right? So you're not going to be taking the subscripts, from the polyatomic compounds because that's not telling you the quantity of the compounds. It's just telling you in this example that there are 3 oxygens, right? It doesn't tell you that there are 3 nitrates. So you wouldn't take this 3 and go up and across. See what I'm saying? So you're just going to do it with the subscript that tells you how many of that compound there is. Okay? Anyways, just wanted to explain that real quick. So we're going to split them up. We're going to do the exact same thing with this. Something that I also want to point out is the cation always goes first, you guys. The positively charged ion always goes first. Cation first, anion second. All right, positively charged first, negatively charged after that. So we're gonna do the exact same thing with this. If sometimes you don't see a number, that doesn't necessarily mean that it's a 1. Sometimes it could be that the numbers crossed out, right? If they end up being the same number, they will cross out. So you just gotta be careful with that. If you don't see any subscripts, then you just gotta make sure that you at least know one of those 2. So in this example over here, we have sodium that we know has a charge of what? Or do we know that? What? How about hydroxide? Do we know hydroxide? Negative 1, right? That's probably the one that we're supposed to memorize. So we have hydroxide that we know is negative 1, right? And then we've got, let me keep the same colors actually. All right, and then we've got Na. If this is negative 1, right, we don't see anything here, which makes sense. Then whatever this was, we would see it down here. And we don't see anything there, so that tells us that Na is what? +1, okay? Alternatively, you can also think about it as hydroxide got a charge of negative 1. I just see that there's just 1 sodium interacting with hydroxide, so therefore in order to cross that out, that must tell me that sodium's got a charge of +1. Okay? So I'm gonna take that. After you do this, all you've gotta do is write down the positive of 1 or the cation of 1 next to the anion of the other to generate the first product. So I'm gonna write Fe +3 and then OH. The final formula, you guys, does not have charges. So I just like to write them next to each other first before I write the final product. I have noticed that the students that take this extra step make less mistakes, okay? Unless you've done this many, many times, hundreds of times, maybe you want to take the time to write this step so that you don't mess up. Okay, so I write them next to each other, then I just do the crossing. So I'll take that down and across, down and across. My final answer is gonna be iron, that 1 which we don't write, and then OH. And because we have a polyatomic ion, we want to write the parentheses. If I don't write the parentheses, it will be incorrect. Because if you don't write the parentheses, you're just telling me that there are 3 hydrogens, when in fact there are 3 hydrogens and 3 oxygens, right? So you want to write the parentheses every time that you have a polyatomic ion and you're going to be placing a subscript next to it, okay? So that's our first one. Alternatively, you could look at this, right, and say, okay, if I know that the charge of iron is +3 and I know that the charge of hydroxide is -1, well, how many of each would I need in order to have a net charge of 0, right? So if you have a +3 and a -1, then you need 3 negative ones to cross out 1 + 3, right? So we need 3 hydroxides to cross out 1 iron in this example. Does that make sense to you guys? All right. So there's how we write the first one. The second one, I'm gonna have the positive of 1 with the negative of the other. The one that I'm gonna be writing down first is going to be the positive one, and they're both 1 or charge of +1 and -1. So you don't really have to do the crossing, right? You can just look at it and know that you're gonna have Na and then NO3. Okay? Questions there? We good? All right. So I'm gonna then get rid of this below, and I'm gonna balance them. So when you balance them, notice that the polyatomic ions continue to be together on the reactant and the product side, right? So over here on the reactant side, we see an NO3 or nitrate, which continues to be NO3 over here. We have hydroxide, which again stays the same on the reactant and product side. For that reason, when you're balancing them out, since they're staying together, you could just write down the polyatomic ion as opposed to split them up. If you split them up, for instance, if you just do O and then H, you could certainly do that. It's just that it's going to take you much longer and you're more prone to make mistakes. So there's really no reason of taking that extra step. Just keep them together. So let's do that. We have iron on this side. We've got nitrate. Sorry. Na and OH. What I have on the reactant side, I'm also going to be having on the product side. So I'm going to take that, copy it, and put it over here. All right. So when you do that, now we're going to count how many there are of each. So for iron, we've got 1 on the reactant side. How many on the product side? Just 1 as well, right? How about nitrate on the reactant side? 3, and the product? Just 1. And for sodium on the reactant? Just the 1, right? And then on the product, 1 as well. Hydroxide, 1 on the reactant, and then 3 on the product. I recommend that you guys take this extra step to write them down like this. Same reason, unless you do a whole lot of practice, you're more prone to make mistakes if you don't have it visually presented in front of you. If you're just doing the math on the equation, it can get messy really quick. All right, so now we're going to make the match. So we have iron 1 and 1, that's good. Nitrate 1 versus 3. So I select the lesser number, which is 1. 1 times what equals 3? Easy? 3. So this now becomes 3, but because I also placed that in front of sodium, that's going to be impacted as well. Now this is 3 because it used to be 1. Now we have 1 versus 3, same thing, right? Select the lesser number, 1 times what equals 3. The answer is 3. And I put that in there. Now we have 3. And because I placed that in front of hydroxide, this is also going to be 3. So now I have 1, 1, 3, 3, 3, 3, 3, 3. We're good. Questions on how to balance? No? Okay. So after that, you guys, we're going to identify the solubility rules of the product. So again, for our precipitation reaction, we have 2 aqueous ionic compounds that are going to interact to form an insoluble product. So that already tells me right there that my first 2 reactants are going to be aqueous, right? For purposes of this example, let's still look at the rules. And just so that you guys know, I believe these rules are going to be given to you, is that right? For lecture. So if this is given to you, this is really an opportunity to get this right. You shouldn't get this wrong when the answers are given to you, okay? You're basically just gonna take your time, read through it until you find a rule that applies. Once you find a rule that applies, you don't have to keep on going because the rules are not going to be contradicting themselves. So once you find a rule that applies, move on to the next, okay? So let's look at the first one. We've got iron and nitrate. So let's look for nitrate in here. Number 2, all salts of nitrates, chlorates, and acetates are soluble. If it's soluble, I'm going to be writing an AQ for aqueous. Okay, it's an aqueous solution. AQ. Sodium hydroxide. Rule number 1, all salts of group 1A and ammonium are soluble. So AQ, which is matching with what we already knew, right? The first one, we have iron and hydroxide. So I'm going to be looking for a rule of hydroxides here. Number 6, all oxides and hydroxides are insoluble except for those of group 1A, calcium, strontium, and barium. So it's going to be insoluble, which means if it's insoluble, it's going to be generating solid, right? So I'm going to be writing a little S to represent that. Then we have NaNO3, so the first two rules, right, that we already discussed. All salts of group 1A are soluble, and then all salts of nitrates are soluble, so AQ. All right. So this makes sense. We have two aqueous ionic compounds that react to generate an insoluble product. All right, so we have there a precipitation reaction. If you did this and this one ended up, instead of an S, right, instead of a solid being AQ, then you would say no precipitation reaction occurred. Okay? Yes, ma'am.
So does it have to be two insolubles? Two solubles to make it insoluble, or can it be like one insoluble and one solid? You know what I'm saying? Like.
So what this is basically saying is that if you react, so if you have these two reactants, you mix them up, you're going to see a solid forming. And normally you're not just gonna have like two aqueous, right? Two aqueous solutions just give you just one solid, right? You're usually going to have a solution which will have that solid particles there, right? That pellet, or solid particles suspended, usually in an aqueous solution, which would be the supernatant. So in other words, what I'm saying is, if you had a test tube, if you were to see this on a test tube, the solid that you would see will be this, and then if you see the aqueous part, it's going to be this.
Okay.
Like the supernatant would be this, sodium nitrate, and then the solid particles are going to be iron 3 hydroxide.
Okay.
Did that answer your question?
Yeah.
So for it to be a precipitation reaction, you must have one solid form in here. So kind of like what I was saying, if you were to do this in lab, which we will be doing some in lab, this solid, you might see it very evidently. Sometimes you see little chunks, like a pellet forming almost. But other times it's not going to be as clear. It might look like a cloudy, like solution becomes cloudy. Well, the reason the solution becomes cloudy is because you have little solid particles suspended in a solution, right, in an aqueous solution. So if it's cloudy, if something becomes cloudy today, know that it's because there's a solid form in there, right, little solid particles. Some of them are going to be more obvious than others.
And then we can check it by doing that.
And then, exactly, and then you're going to, based on what you're seeing, if you're like not 100% sure, you can also do this and confirm. So if you're like looking at it and you're like, I don't really see a change, let me look at the products and see if that's matching my observations, and it should match. Okay. With that said, it could have a color. Well, let me stop myself so I don't confuse anyone. Okay. Questions here? We're good? All right, new territory, guys. Let's talk about oxidation reactions, aka redox reactions. That's my little abbreviation for reactions. So in an oxidation reaction, what it is the transfer of electrons from one element to another, all right? So essentially what we're seeing is electrons moving between atoms. If you were to look or write a representation of that, right, you could have something like this. Right? We have an electron literally being transferred or moving between two atoms. So let me write that down for you guys. Electrons moving between atoms. All right? So, given that electrons are negative, like we've kind of discussed when we were talking about Lewis structures, right? Electrons are negative. If you're losing electrons, you're becoming more positive, right? Those electrons, more positive. And if you're losing electrons, you're said to have been oxidized. So this is known as oxidation. Okay? Let me write this down. If you gain electrons, you become more negative, and that is reduced. It's almost like an oxymoron, because sometimes if you think of something being reduced, you might think of having less of. So you're gaining electrons, but the term is reduced. So there's an acronym to help you guys with that, and there's really two. One of them, or that I know of at least, one of them is going to be oil / rig. When I learned this, oil was easy to, I guess, memorize because it's already a word that you know, right? So oil is oxidation is loose, and if you know oil, then you know that then the opposite, right, then will be reduced. So if oxidation is loose, then gain must be reduction. Okay? So if you remember oil, then you'll know the other one, right? Then there's this other one that is Leo / Ger. Have you guys seen this one in lecture? And they say Leo the lion goes Ger. Okay. Anyways, either or, whichever, just learn one, okay? So we're going to be doing, as an example, this guy right here. We have to be familiar and understand the oxidation number rules. Now, I'm going to give you guys a little shortcut. If you've got your periodic table, this is how you can easily remember the charges. All right? Pay attention to this. So on the first column, this is likely to lose 1 electron, so +1. Likely to lose 2, +2. We're going to skip the transition metals. We're going to resume over here, +3. Then where carbon is, you're going to think of this column right here as a mirror. What does a mirror do? It will reflect, right? The opposite. So if we are looking at this, right, reflecting the opposite, we have 3, 2, 1. And on this side, we have the positive. So on the other side, since it's the opposite, it's going to be negative, right? -3, -2, -1. Okay? So again, 1, 2, 3, mirror, -3, -2, -1. Easy, right? To remember. There are, if you're looking over here, the rules really merge. So for instance, over here, fluorine has an oxidation number of -1. Where's fluorine? Right here, right? -1. Oxygen has an oxidation number of -2. Where's oxygen? Right here, right? -2. So it's an easy way to remember. There are some exceptions. So for instance, over here, oxygen says -2, except in peroxides, where it has -1. So that's just something to remember. Likely, more than not, you're not going to be encountering peroxides, but it is something to be aware of depending on how tricky your lecture professor wants to be in exams, okay? Hydrogen has an oxidation number of +1. What do we see, right? +1. And then again, it tells you an exception, except in metals where the hydride is -1. Then it says the main group of group 1 is +1. That's what we have here, right? Then the main group in number 2 is +2, exactly what we have here. right? And then the halogens in binary compounds with metals have an oxidation of -1, which that's what we have right here. Okay? So if you remember this, it's going to be much easier. There is the first two rules that I didn't go over. So the first one, and they're pretty easy. The first one says the oxidation number of any element in its free state is 0. So it's going to be 0. Okay? If an element is by itself, alone, it's going to be 0. And then the oxidation number of an atomic ion is equal to the charge on the ion. So remember before when they were giving you a compound and then it had a net charge? So it's saying you're going to add all of those up, and if it does have a net charge, it should be equivalent to that net charge. So this is kind of resembling what we discussed before with formal charges. Okay? Questions so far here? All right, so far we just discussed it. So what are we going to do? We've got potassium. It's by itself, so what's going to be the oxidation number? 0, right? By itself, by itself. Then we've got potassium and Cl, so it's a compound. Potassium is in the first group, which is going to give us a what? +1, and then we have a halogen here. It's going to give us, let's see, Cl, -1, right? -1. All right. So here we've got it. In order to write half reactions, which we're going to discuss right now, you're going to be focusing on each element at a time. All right, so let's do that. We're going to have potassium. And then we've got potassium over here, right? And we're just going to be, we already did it because we did the oxidation numbers on the top, but we'll write them down here as well. All right, so first off, again, we're focusing on each of them at a time, and we're seeing that potassium's got 0 on the reactant side and then +1 on the product side. So in this case, you're becoming more positive because electrons are negative. If you're becoming more positive, are we gaining or losing? Losing, right? So it's becoming more positive. And if it's becoming more positive, it's losing electrons. So if it's losing electrons, oxidized or reduced? Oxidized. Okay? Because oil, right? Oxidation is loose. Then, when you're doing this, you identified that it was losing electrons. How many electrons did it lose? 1, right? So if it lost 1 electron, you could think of it as it being spit out of the reaction, right? So if it's being spit out on the reaction, it's going to be represented on the product side, right? Because it's coming out, right? It's being spit out. So you're going to write that down here. All right? I'm sorry. What am I doing? You're going to write down up here. Okay. All right. So this for me, normally, right, you would think of it as, okay, you've got potassium here. It's losing, so -1 electron, right? But in chemistry, we don't really write subtraction in a chemical equation. Therefore, because it's losing, again, you think of it as it's coming out or it's being spit out in the product. All right. So for Cl, it started out being by itself, so 0, then it ended up being -1. This is all what we've already discussed up here, right? So it went from 0 to -1. It became more negative. Electrons are negative. This became more negative. So did it gain or lose? Say confidently. It gained. Right? It gained electron. If it gained electron, reduce or oxidize? Reduce, right? All right. So it gained an electron. just one, right? So if it gained an electron, it's gaining it on the reactant side, right? So you're gonna write that then plus 1e. Okay. So how could this be summarized? Well, you're gonna write, sorry. You're gonna write electrons on the product side. If you're losing electrons, and then what am I right? I'm all over the place today. Write electrons, okay, on the product side, okay, and then write electrons on the reactant side if you're gaining. Okay. Do we understand this? So again, if you are losing electrons, think, okay, it's being spit out in the reaction, so it must come out in the product, right? If you're gaining it, it must be gained on the reactant side. That's one way that you could think about it. All right, let's do one more, shall we? We've got this one right here. And it was already balanced for me. So this is the balanced one, okay? So first off, let's look at what is happening. So we've got by itself, so what's the oxidation number? If they're by themselves on the free state? 0, right? And 0. We're good there, right? They're together here. So let's see. For Mg, what's the charge? Or I should say oxidation number, right? What's the oxidation number? What is it? +2, right? And then for oxygen, -2. Okay. When we are writing the whole, when we're writing everything, when we're writing the half reactions, we also want to take into consideration the coefficients, okay? Because the coefficient is telling me how many of that compound are needed to react, okay, with the other reactant, and how many are being produced, okay? So we have 2 magnesium. We're gonna be looking at all the charge, right? You could think about it as charge or oxidation number, whatever. So we've got 2 magnesium, oxidation number 0, so 0 twice. So 0 times 2 is what? It's still 0, right? All right. We just got 1 of O2 or dioxygen. Then for magnesium, we've got 2 plus 2. So what's the total charge here? 4, right? Because 2 times +2 is 4. Okay. And then we also have a 2 in front of this oxygen. So 2 times -2, -4. Okay. All right, now that we know that, we've analyzed this, right? To write the half reactions, I'm going to do the exact same thing, and I'm going to be looking at one of them each at a time, okay? So, magnesium, starting out. We have Mg, and over here, we became 2 Mg, right? Well, we had 2 Mg, and then we still had 2 Mg. Okay? Then, for oxygen, we just had 1 dioxygen there, and then just 2 O on the product side. Okay. So far, so good, right? No questions here. Okay. All right, so now let's look at them just like we did before. So it's by itself, so we already said that's 0, right? And then over here we identified that it was plus 2, but we said that there's 2 of those, so really it's gonna be plus 4, right? Questions here? So it went from 0 to plus 4. So did it gain or lose electrons? Lost, right? It became more positive, so more positive. It lost. And how many did it lose? 4, right? We went from 0 to plus 4, so it lost 4 electrons. If it's losing electrons, do I write them on the reactant or the product side? The product, right? Plus 4E. Right? That's simple. Again, we're going back to what we've discussed on the top, right? These rules right here. Then, looking at oxygen, we had 0 starting out, right, because it was by itself. Then we ended up having 2O. So we know that oxygen is -2, but there's 2 now, so this ends up being -4. So going from 0 to -4, gain or loss? Did I gain electrons or lose electrons? We gain electrons, right? Gain electrons. If I'm gaining electrons, am I being reduced or oxidized? Reduced, right? It might take a little bit of practice for you guys. Maybe what you want to do is write these top rules that I wrote up here, and as well as the acronym here, and then just take your time doing it and refer back to those while you keep on getting more comfortable. Yes, ma'am. Any questions? Oh, okay, sorry, I thought there was a question. All right, so it's being reduced. All right. If it lost 4 electrons, if it gained 4 electrons, do I write that on the reactant or product side? Reactant, right? Plus 4E. All right. And that's it. Questions? So we said that because this one is losing electrons, oxidize or reduce? Oxidize, right? Because oil. Oxidation is lose. So this is how you will break it down. So make sure that first it is balanced, okay? Make sure that it's balanced first of all. And then write yourself a little cheat sheet looking at the periodic table. Again, really easy, right? 1, 2, skip transition metals, 3, mirror, and then -3, -2, -1. The ones that are by themselves, write a 0. And then if you've got a coefficient, make sure that you multiply that oxidation number by that coefficient. Okay. Questions? Say again? Any questions, you guys, on these? Feeling confident? Feeling experts? Maybe not experts, but confident. All right. All right, guys. And also, if you did this correctly, right, what you should see is if you added this up, right, you should end up with these. Okay? Because this crosses out, right, crosses out, and then this ends up with that, and then this ends up being that. All right. Okay. Now, we've got, yes, ma'am. All right. Any final questions on these? Yes, ma'am.
So the first side is always going to stay 0.
The what side?
The under the first side of the arrow.
So it depends, but if it's by itself, if the element is alone, in solo, then it's a 0. It's said to be in its free state. If they're giving you something with a net charge, remember then what? So the way in which you might see questions like that is if they give you a polyatomic ion and then they give you a net charge and you don't know what one of those charges are going to be from the periodic table, like if you didn't know, you could use that to figure it out. So I'm thinking if, not 3, negative. I don't want to confuse anyone, so it's not. All right, so here we have single displacement reaction again, like we've been doing. Oxidation reaction, right? And there's also a way to find out by looking at it, by looking at the compounds and the elements, if the reaction will take place or not. Some of the reactions you're going to be doing today on part 2 for single displacement reactions are not going to take place, all right? There's actually one. So how do you know? The element that is by itself, so the free state element right here, the elemental iron, would have to be more reactive than the metal in the compound. So for the reaction to take place, the one that is by itself will have to be more reactive than the one over here in the compound, so that it can take over. And you can kind of think about it like, you know, you've got calcium and Cl are in a relationship, right? They're boyfriend and girlfriend. And then you've got iron over here that really likes calcium's girl, wants to take over, right? But why would Cl leave? Like, iron has to be given something a little more, right? It's going to have to be a little bit more reactive than her current boyfriend for her to want to leave him, right? It's one way that you can think about it. So, given that, how do we know? We're going to have, or you guys should have this chart right here, and the chart is increasing in activity, right, or reactivity. So, you want to find them both in here. So, the one by itself, again, so it's increasing. Oops. It's increasing, true. So let's look at it. We've got calcium is right here, and we have iron right here. We said that the one by itself, right, the one that's single, has to be more reactive than the one in a relationship in order for the reaction to take place. So looking over here, we have calcium and iron. Calcium is more reactive, right? It's higher up. So if calcium is more reactive than iron, is the reaction going to take place? Is Cl going to be leaving the current boyfriend to go with iron? No, right? This fella is boring. It's not reactive enough. So it's gonna stay with calcium, okay? No reaction will take place here. So again, in order for a reaction to take place, the single element is going to have to be more reactive than the compound element or metal, okay? So no reaction here. Questions? I think that's it. Any questions about anything we've discussed?